Okay, so welcome to lecture 4 on the proof complexity as a computational lens course. So, quick recap of what we did last time or what we've done so far. We're looking at the resolution proof system, and we're doing lower bounds for the first 3 lectures. We had the pigeonhole principle formula, and then last time we did taking formulas. And what we did was we analyzed resolution proofs using the prosecutor-defendant game, where the prosecutor was asking questions about values for variables. Defendant was claiming that the CNF formula was in fact satisfiable, claimed to have a satisfying assignment, and an efficient prosecutor strategy corresponded to a short resolution proof, whereas a successful defendant strategy that proved that in order to have a winning strategy, the prosecutor needed to write down lots of different information, corresponded to a resolution lower bound. And although we did not prove this, this is has been more or less left as an exercise. Well, we did one. We sketched the direction that a resolution proof would give a good prosecutor strategy. We did not sketch the opposite direction, that in fact a good prosecutor strategy is exactly a resolution refutation, but this is a characterization. So the prosecutor-defendant game is exactly a resolution. It characterizes resolution. And so what this means is that in principle, as soon as you have a resolution lower bound, there is a defendant strategy hiding in there somewhere. However, it might not be that making this defendant strategy explicit might not be the easiest way to prove resolution lower bounds. And in fact, most of the time it is not. So we will focus from now on mostly on other lower bound techniques. So let me talk first. I'll mention one technique that is super important that we'll get to in a bit, is to look at resolution width. Okay? It will turn out that it's very convenient to study the size of clauses in a resolution proof, and if we can get a really good lower bound on resolution width, then that's actually an easier way of getting the lower bounds we struggled a little bit to get so far. Another proof technique, and this is what we'll talk about today, is to reduce the whole problem of lower bounds to circuit complexity. I'll use something that is called interpolation. And that's the focus of today. So we'll do a resolution lower bound by using so-called feasible interpolation and reducing the whole problem to circuit complexity, to Boolean circuits. So I think hopefully many of us have seen circuits before. Let's just make sure to go over the preliminaries, make sure we're all on the same page. So we have, in our Boolean circuits, we have 3 types of gates. We have AND gates, we have OR gates, and we have NOT gates. And the fan-in will focus on fan-in 2 for AND and OR, and obviously a NOT gate has fan-in 1. All the source vertices, so a circuit is just a directed acyclic graph, a DAG with a single sink, and every source is labeled by an input variable. So here we have a circuit that takes variables x1 and x2, and every internal node now, every gate, will compute the function that it is labeled by on the input edge. Okay? And if we just define this bottom up, then here is the sink. It will also compute some Boolean function. of its inputs, and that is going to be the whole Boolean function computed by the circuit. Okay, so for instance, just to warm up, we can see here what is this computing. Well, this circuit will be true if it's an OR. So if one of these AND gates is true, and the first AND gate wants x to be false, x1 to be false, and x2 to be true, the other AND gate would be happy with x1 being true and x2 being false. So as you already figured out, this is just x1 XOR x2. Right? The second gate, second circuit, sorry, is just computing majority of x1, x2, and x3. It will output 1 if and only if at least 2 of the inputs are 1. What we care about now, we care about size of circuits. So that's just counting the number of nodes. So the size here is 1, 2, 3, 4, 5, 6, 7. Yes, this is 1, 2, 3, 4, 5, 6, 7, 8. We know that it's not so hard to show that any Boolean function on n bits can be computed by a, so let me maybe write this down. So any Boolean function on n bits is computed by a circuit of size, it's easy to get something like n times 2 to the n. And basically you can just write down a CNF formula or a DNF formula that will compute your function. Look at the truth table. In fact, you can do slightly better than this. You can do 2n over n. That requires some work. Right now, circuit complexity is just given different Boolean functions or families of Boolean functions, try to pin down how complex they are, how complicated circuit do they need. Okay, and this was also conceived as circuit complexity, just as proof complexity was originally conceived as a line of attack against P versus NP. Just as proof complexity, it hasn't been terribly successful at reaching this original goal, but there's lots of very beautiful math that has been done. Lots of interesting results have been proven for. So we don't know, I mean, we know, in fact, that 2 to the n over n is the right bound for most functions. Like if you just pick, like a typical Boolean function requires very large circuits. But when it comes to explicit lower bounds, we cannot prove anything superlinear, which is very annoying. And even getting the constant, even getting I don't even remember for and or not, if the current state of the art is something like 5 times n or something like this, is the best lower bound we have, which is a little bit depressing. What we can do is we can look at restricted types of circuits. You can look at circuits of bounded depth, where you limit the length of the longest path in the circuit. Or what we're going to do today, we're going to look at monotone circuits. So suppose now we have two vectors x and y, bit vectors, n bits. Let's say that x is less equal y if in all positions xi is less equal yi. Right? So just a coordinate-wise comparison. So I say that a Boolean function is monotone if whenever x is less equal y in the sense, this means that f of x is less equal f of y. Or phrased differently, it can never be the case that f can flip from 1 to 0 by flipping an input bit from 0 to 1. And we say that a circuit is monotone if it has only AND gates and OR gates, but no NOT gates. So this is a monotone circuit. Majority is a monotone circuit. And the other two circuits that we have on the board, we'll talk about the third one in a bit. You can start thinking about if this is going too slowly, you can think about what function this is. And it's a simple fact that f is a monotone function. F is monotone if and only if it can be computed by a monotone circuit. We're not going to prove this, but it's not hard to prove. Okay. The third function that we're going to talk about today is this body over here. And just because it's boring, if I do all the talking, can anyone tell me what this function is? It's a multiplexer. Multiplexer. Yes. So what is it computing?
If x is 0, then it sums through y, and if x is 1, it sums through z.
Exactly. And I will call this a selector function, just to be consistent with my notes. So indeed, it looks at x and lets x select the output. Right? So if x is 0, then the result will be whatever y is. And if x is 1, then it will be whatever z is. And again, this is not a monotone function. But we're going to be interested in this function anyway. Okay, good. So now we know enough about circuit complexity to go back to proof complexity. So we're going to talk about interpolation. This was something that Jan Krajicek came up with in 1994, and Pavel Pudláks used it in 1997 to prove lower bounds on clique-colouring formulas. And Pavel Pudláks actually proved the lower bound for the cutting planes proof system. We'll get there in a bit. I mean, as we know already, cutting planes is a much stronger proof system than resolution. And in order to make our lives a little bit easier, as a warm-up today, we'll stick with resolution for a while yet. And we'll do Pavel Pudláks' lower bound, but we'll do it for resolution, and then hopefully later in the course we'll do it for cutting planes. Okay, so what is the clique-colouring formula? Clique-colouring formula comes with parameters. Namely n, which is it speaks about the existence of graphs, and it talks in particular about the graph with n vertices, and then it talks about there's a parameter m, which is the size of a clique in the graph. And what the clique-colouring formula says is basically that there exists an n vertex graph which has two wonderful properties. Namely, this graph has an M clique. And simultaneously, it is M minus 1 colorable. And there aren't many such graphs. And so this, if we encode this into CNF in an appropriate manner, then this should be unsatisfiable. Okay? So how are we going to do this? So let me introduce the notation we're going to use today. So we have sets of variables, and I use arrow notation, at least in the beginning, and then maybe I'll get lazy later on. So variables Pij, for 1 less equal I, strictly less than j, less equal n, we'll think of these as edge indicator variables. So if I assign these variables, that specifies the edges in the graph. I'll also have a set of variables q, and I will think of them as identifying a clique. So k will identify members of a clique and map them to, so basically qki is true if clique member k is the ith vertex. And then I also have variables RIL to describe a coloring. And here I again ranges over the vertices. L ranges over the colors. And the meaning of RIL is vertex I has color L. Okay. So so what are the clauses in my formula? Well, they're going to be the following. So for every k from 1 to n, I will say that there is a k clique member. So for every k, a big O over all the vertices, some vertex is the ith clique member. And then we're going to say that for k distinct from k prime, or really k, you can write less, strictly less than k prime, we're going to say that the clique members are different. So the k clique member and the k prime as clique member are different vertices. And finally, what's the property of a clique? Well, we say that if ij is not an edge, then either I is not in the clique or j is not in the clique. Okay, and I'm a little bit lazy here and I'm skipping exactly how we sum, but I hope this is more or less clear. So the way you read this is that if j is the k primeth clique member and I is the kth clique member, so I and j are both in the clique, then ij had better be an edge. Okay, so this is the clique part of the formula. And then I also say for every vertex, I do a big OR over all the colors. And I say that vertex I has some color F. And then finally, I say, well, if Pij, if Ij is an edge, so if Pij is true, then it can't be the case that I and J both have the same color edge. And so neighbors, here we say that cliques, vertices in a clique are neighbors, vertices with the same color are not neighbors. That's the formula we're going to work on. And now, the observation that we're going to use is we're mostly going to forget what this formula looks like today. We'll keep it in mind for a little bit longer, but we'll mostly forget about it. But we will note that the clique-colouring formula can be written on the form. It decomposes into two formulas. One, a formula over only P and Q variables, and then one B formula over only P and R variables, right? So here is our A formula, and here is our B formula. And now we are going to do something that we should have done maybe long ago, and that we'll talk about more later in this course. We'll start talking about restrictions or partial truth value assignments and how they affect formulas. So suppose, and let me do this again mostly by example. So if I have a formula F and a partial truth value assignment, which is, I will refer to as a restriction rho, then F restricted by rho is the formula you get by basically you remove satisfied clauses, and you also remove falsified literals. Just to make sure we're on the same page, let me, and since I think it's the first time we're formally finding restrictions, let me do like a small stupid example. X or Y, and X or not Y, and not X or Y, and not X or Z, and apparently not Y or not Z. Suppose this is my formula, and now let me consider the restriction that just takes Y and sends it to true. So in that case, let's see what happens. Then F restricted by rho is the first clause vanishes because it's satisfied. In the second clause, we remove Y, so we just get X. The third clause, we get not X.
Finish this.
Wait, so let's see. I am out of sync with my notes. Let's see. This is satisfied. There we get X. This vanishes. Great. Yes, that's why I'm out of sync with my notes. I was just checking whether you were awake, obviously. The fourth clause is not affected at all. And the fifth clause, we just pick up not set. Yes? And now here comes the interesting thing. Okay, so first, let's make a few simple observations. Suppose that F is unsatisfiable. And let rho be any restriction. And obviously F restricted by rho is still unsatisfiable. Otherwise it would be super surprising. And now let's look at this formula. A over P and Q variables and B over P and R variables. And suppose that rho is a restriction that sets all of the P variables. Well, let me actually introduce, from now on, let me introduce so we have A, P, Q restricted by this rho. I will just, from now on, to save some typing, I will just plug in rho here instead of the P variables and Q. And in the same way, B over P and R, let me just, restricted by rho, let me just plug in rho and write it in this way. Let me just introduce this notation to type less. It's here that for any truth value assignment, the interesting thing now is when you plug in rho, you see that this formula decomposes now. This The A formula will now only be over Q variables, and the B formula will only be over R variables. Yes? And at least one of them has to be unsatisfiable, possibly both. And this brings us to interpolation. So an interpolant I for this formula A PQ and VPR is a Boolean function that has the following property, that you take any row which assigns the P variables, and if the interpolant outputs 0, that means that A row Q is unsat. And if the interpolant says 1, that means that the B formula is unsatisfiable. Okay. Note that it could be that both formulas are unsatisfiable. In that case, we just commit to any choice. You can any function that satisfies these two conditions is an interpolant. So interpolants are not unique, but any function satisfying these properties is an interpolant. And clearly interpolants exist because this is you could define the interpolant to say like always pick A if that's possible, otherwise pick B, something like this. So now we decided on a function. Any function has a Boolean circuit. So interpolants exist in terms of like for any interpolant there is a Boolean circuit computing an interpolant. And then I can relax it, and then maybe there are many different interpolants, and then I can choose which one I like best. But there is always an interpolant. And now here comes the point, like here's what we want to prove today. We want to prove that if my formula F, APQ, and BPR, if this formula has a short resolution refutation, then it has a small interpolating circuit, a small interpolant. Let me write a small interpolating circuit. Okay. Obviously, we need to make precise exactly what we mean, but this is what we're going to do today. Okay? So if F has a short resolution refutation, then we're going to be able to construct from the resolution refutation a small circuit that computes this. Does this make sense? Okay, and now, like our plan is to do the following. So we're going to use this. So here's like our high-level proof strategy. What's going to happen today? So first we pick our formula F, and this we kind of already did. We want to look at the clique-colouring formula. A, P, Q, B, Q, R. B, P, R. Okay. And now we assume that there exists short resolution refutations. And now, by using this theorem that we need to prove, we deduce that there exists small interpolating circuits. But now we set things up so carefully that we argue that the interpolant computes something for which we have a lower bound. lower bound. Okay. Well, then we get a contradiction. That was an ugly contradiction. That was meant to be some kind of zigzag, maybe like this. This is a contradiction, and this means that there doesn't exist short resolution refutations. Or in other words, we have proven a resolution lower bound. That's the game plan. Does this make sense? Okay. And now let's take a step back. Like you can talk about in general, you can look at different proof systems, and you can say for which proof systems does this work? And for proof systems where this does work, they are just introducing a piece of terminology. They have feasible interpolation. So any proof system for which you can carry this out is a proof system that has feasible interpolation. What we're going to prove today is that resolution has feasible interpolation. What Pavel Pudláks proved was that, in fact, cutting planes has feasible interpolation. Now, there's going to be some twists here because the question is like, what kind of computational object are you going to extract? Today, we're going to extract standard circuits. For cutting planes, we get slightly more expressive objects. And then there are other proof systems for which you also have different types of interpolation. And then there are certain proof systems that we believe do not have interpolation. Okay. However, resolution, what we're going to prove today is that resolution has feasible interpolation. Okay. And then we're done. Except we have a little problem. If you paid attention to what I said in the beginning, we just need a circuit lower bound. How good are we at proving circuit lower bounds? Not terribly good. So, this is a problem. But what we're going to do is, so let me write this down even, that the problem is that we don't have good general circuit lower bounds. That's like a real problem. It's a bummer. So the way we're going to fix this is we're going to extract monotone circuits. Because for monotone circuits, we do have lower bound. Okay, except that for most of today's lecture, we're actually not going to extract monotone circuits. We're going to extract, I'm getting a little bit ahead of myself, but we're going to extract circuits with AND gates, OR gates, and selector gates. So I'll have ternary gates that take X, Y, Z. And this is obviously still a Boolean circuit because anywhere I have a selector gate, I just plug in this thing, right? Okay, good. But now you see that the problem is that this is very non-monotone. We have a NOT gate here. We're just going to ignore this. Don't worry, okay? For most of today's lecture. And then towards the end, we'll argue how to fix this. So we'll start working with selector gates and just ignore questions of monotonicity, and then we'll make a mysterious hack towards the end, and things will be fine. And by then you will be like bored and tired enough not to pay too much attention, so I'll get away with it. That's the plan. Okay. So let me now actually, okay, I want to erase the clique-colouring formula now, but before I do that, let me observe one thing here, that I want to talk about the p variables, the shared variables in the clique-colouring formula. Where in the A formula do I have my p variables? Only here, right? Note that they are only positive. Yes? And in the B formula, you see that they're only negative. Okay. So I'll write down this carefully in a little bit, but due to my poor board technique, I'm about to erase this now. So I wanted to make this point before I erase this formula. It will turn out that feasible interpolation for resolution will always work, but that's not very helpful because we'll get a general circuit. Feasible monotone interpolation will work when one of these conditions hold. When P is only positive in the A formula, or when P is only negative in the B formula. Okay, and I'm just, now we stare at this formula and you agree with it. Actually, here both of these conditions hold. Okay, good.
You only need one.
I only need one of them. Yeah. Okay. So good. Now I'm actually not. Now we can forget about this formula because now the rest of the proof is going to be. Actually no. Let's see if I can keep this formula while writing down the. We're going to use the circuit lower bound. We're going to use as a black box. It's not too hard to prove, but it would take us. I don't know. At least half a lecture more, maybe closer to one full lecture. It's a nice result. Sometimes we do it in the computability and complexity course in Copenhagen in spring. So maybe this year, if you bug me enough, I'll do it. Or maybe not. But we're going to use the following theorem, which is due to Razborov and also Alon-Bopana. Razborov is, according to my notes, in 85, Alon-Bopana 87, so this is one of the classics. And the theorem says the following, that we have a circuit computing on graphs, and we're going to represent the n-vertex graph G by n choose two edge indicator variables. Right? Just actually the p variables, you can think about them. So think about the circuit computing on graphs. How is it given the graph? By n choose two edge indicator variables. Okay? And let's suppose that m is something like the fourth root of n. Then, for these parameters, there is no monotone circuit of size less than exponential in square root n. So there's no size, no circuit of size smaller than exponential in square root n that can distinguish the following two cases. Case A, G has an M-clique. Case B, G is M minus 1 colorable. So any circuit, clearly there are circuits that solve this, and note that there are monotone circuits solving this, because clique is a monotone problem, right? If a graph contains a clique and you start adding edges, then it will not be the case that the clique suddenly disappears. And coloring is like an anti-monotone property. So there are monotone circuits for these problems. Definitely. But in an n-vertex graph, it requires exponential size for monotone circuits to distinguish whether there is a clique of a size essentially fourth root of n, or whether the graph is colorable with one less color. Okay, so we'll just use this as a black box. And now, the point is, the connection that we need to make, why I wanted to keep the clique-coloring formula on the board, is that suppose we have a resolution proof so that we extract an interpolant, and suppose we plug in a graph that has an M-clique, or is M-1 colorable, then the interpolant will tell us which of these formulas are unsatisfiable, right? And if there isn't a clique, then this formula is unsatisfiable. If the graph isn't colorable, then this is unsatisfiable. So the interpolant will solve this problem for us. Right? But if it is true that I can do this, and in contradiction, in addition, that I can get monotonicity here, and this will show that I will be able to take this circuit lower bound and turn it into a resolution lower bound. Does this make sense? This is sort of the, maybe it's worth it to think for a few seconds as well.
Are the outputs flipped? Like, because when there is an M-clique, it should say 1 or am I getting this mixed up?
Did I flip the signs? Excellent question.
When the interpolants,
I'm just saying that, the
interpolance is 0, A is unsat, therefore there is no clique. But you cannot guarantee that it's M-1 color.
Yeah, I think, the interpolant here will output 0 if there is no clique, right? And then as you add more and more edges, there will appear a clique. So I think the signs are probably right.
Okay.
So here I basically say, if there is a clique, then I want output 1. If it is M-1 colorable, then I want output 0. Okay? And the point is, I'm using the promise, right? So I'm saying that I'm giving you only a graph. So note that this is we actually need it, like I won't elaborate too much on this, but we're actually using it that we have a promise. I promise to you that the graph will be in one of these two cases. Okay? It will either have an M-clique or be M-1 color.
Mm-hmm.
And then, if it is M-1 colorable, then B is satisfiable. So the interpolant has no choice but to answer 0.
Okay, then you're
okay. And if there is a clique, then the A formula is sat, so the interpolant doesn't have a choice other than outputting 1. There could be graphs in between. We don't know about those. But happily, the lower bounds by Razborov and Alon-Bopana say that no. Already, if you promise to me that you only look at these two special cases, then already that is hard for a monotone circuit. But that's a very good point. And I'm trying to get away with sweeping as much as possible under the rug, but so far unsuccessfully. So we're really using the fact that here we're using the promise version of the problem. And then we're using that. Note that in general, we will, in fact, the interpolant will be able to say much more, right? It will also, if it is true that a graph doesn't have a clique but isn't colorable, then the interpolant will still make a commitment, whereas this monotone circuit, we're not saying anything about. So we're not giving any promise about the monotone circuit, but we're saying that even a monotone circuit that takes care of these two very special cases has to be large. And an interpolating circuit definitely does that, plus potentially much, much more. Does that make sense? Okay, but then, okay, if we're happy with this, then this is the last time I think we see the clique-coloring formula today. And so now our game plan what do we need to do? How are we going to use this? So we're going to do two things. We are first going to build an interpolating circuit. From any formula A, P, Q, and B, P, R. From now on, we're not, in particular, the clique-colouring formula fits this pattern, but we can look at any formula that looks like this. And we're going to take any resolution reputation of such a formula, and we're going to build an interpolating circuit. And that's what's going to take most of today. And then we're going to show that this circuit can be made monotone if one or two things hold. The p variables are positive in A, or the p variables are negative in B. So this is actually a little bit funky way to state it. If you realize, everything is symmetric here, right? So actually all I'm saying is if in one of the subformulas the p variables only appear with one sign, that's all I'm saying. But somehow, for some reason, we usually phrase our interpolation results in this way. But really what I'm saying is as if in one of the subformulas the shared variables appear only with one sign, either positive or negative, then we're good. And if you worry about the sign, I'll just flip p to minus p everywhere, and then we'll basically be. Actually, is that true? Maybe what I said is false. Sorry, I take that back. Maybe we have to be a little bit careful with our monotone circuit. Let me actually stick with this. Sorry, I take back what I just said. Happily, it's being recorded, so it will be on the internet forever. I think it would, because we would need to wait. Okay, never mind. This is an okay way of stating it. I don't think it actually matters too much.
I think it's like, it's kind of arbitrary that you say you want one if A is unsat, or you want the 0 if A is unsat.
Maybe, yeah. Yes. Morally speaking, it shouldn't make a difference. Formally, syntactically speaking, I think we want exactly this. So P is positive in A, P is negative in B, or otherwise we might need to flip things around. Never mind. The danger of making unprepared remarks. So now I want to put the theorem. The theorem is going to be a little bit of a mouthful. Let me see if I can write it over here. Are we happy with the selector function?
Yeah.
Let's remove the selector function. Okay, so here comes Pudláks. So in our notes, this is theorem 2 by Pudláks in 1997. And we say something like the following. So how are we going to state this compactly? So we're claiming that A, P, Q, and B, P, R is an unsat CNF formula over disjoint set of variables, P, Q, R. And suppose that pi from A, P, Q, and B, PR derives contradiction. So this is a resolution refutation. In length, so number of clauses, capital N. Okay. So suppose again A and B is an unsatisfiable formula. P, Q, R are disjoint set of variables. Pi is a resolution refutation. Then the following holds. We have an interpolating circuit. Of size big O of L, which has the following property that when I just plug in rho, such that for rho, that is an assignment to the p variables. If the interpolant says 0, then A rho Q is unsat. But if the interpolant says 1, then B rho R is unsat. Okay. So, from pi, we can construct a resolution refutation pi sub A that just takes A rho Q and derives contradiction if the interpolant says that this is possible, and otherwise if the interpolant says that B is unsatisfiable, then we're going to be able to very algorithmically, the point is that this is going to be like a very explicit construction. Now, depending on what the interpolant says, we're actually going to be able to take pi and just massage it and extract from it a resolution refutation of either the A formula or the B formula. Okay? And this will again be of length actually strictly smaller than or less equal L. Well, actually strictly smaller, but who cares? Logic. And then the third condition says that if the p variables are only positive in A or only negative in B, then the circuit can be made monotone. Can be made monotone. And then let me just write down that while we have it all in memory, suppose I can prove this, then I claim we're done. Right? So let me write this down because we will soon forget what the clique-colouring formula was. But before we forget, we'll deduce that, well, if we have a clique-colouring formula over n vertex graphs with m chosen to scale like 4th root of n, such formulas require resolution, reputations of length at least exponential in eighth root of f, where from 4 to 8, this is this square over here. Okay? What we're going to do now is our plan is we'll do 2 first. Actually, so the way we're going to do this, we're going to build the resolution refutations. Actually, we're going to build both pi A and pi B in parallel. Okay? We'll just, by forward induction over the proof, I'll build both of these. And then when we get to the end, we're going to take a step back and see which one of them actually is the refutation. Okay? So we're going to then use our construction in 2 to get 1. Basically, what I'm going to argue that we're going to do this very, very explicitly, very concretely. And then once we've done it, we'll just look at, actually, this is so simple that a circuit could have done it. And we write down that circuit. And then we just need to do some hacking to get 3. But sort of morally, 1 and 2 is the hard stuff, and then 3 is a somewhat mysterious hack, which is obviously crucial because without monotonicity we wouldn't go anywhere. But this is the plan. And maybe this is a good place to have a break. Any questions so far, or is the plan clear? Then I suggest that we take a break here. We are back after the break.
And during the break, there was a question from the chat. Has there been attempts to prove lower bounds on resolution reputations of clique-colouring formulas using similar proofs as the games approach we saw for PHP?
That is an excellent question. I don't know. I would guess not. It's maybe at the end of today. It's an interesting question to think about how that would work. I mean, to the best of my knowledge, even for Satin, the proof we did last time, I don't know that anything like that is in the literature. This is something that we cooked up a few years ago, precisely because we were motivated by the question of, well, by the observation that the prosecutor-defendant game exactly characterizes resolution, hence there should be a prosecutor-defendant version of the Satin lower bound. What would that look like? And the reason we were interested in this is that there are, as we will see, and we're getting a little bit ahead of ourselves, but the next 2 lectures will talk about the clique problem. And there actually, all of the other tools that we're going to talk about during this course don't seem to apply. And the only approach we have are prosecutor-defendant games. So you can view as what we did during the first 2 lectures to just develop a feel for this tool, which is the only one we have currently to attack the clique problem. How to do prosecutor-defendant games for this? I mean, it should be possible somehow. It might be an interesting exercise. I don't know how to do it. Okay? So let me talk about what we are going to do. So basically, we have this whole resolution reputation from the A clauses and the B clauses that derives contradiction. And suppose we have a restriction rho prime, then basically we're going to look at how this restriction affects this proof, and we're going to sort of maybe, if it turns out that B is satisfiable under rho prime, but A is not, actually let me call it rho A then maybe, then what we will kind of do is we'll carve out and we'll see that from this part of the proof you actually get contradiction in the restricted formula. Whereas for B, we'll also do exactly the same construction, but we'll just figure out at the end that, oh, this resolution derivation didn't lead anywhere. Okay? But suppose for some other graph B encoded by row B, it turns out that A is satisfiable, but B is not, then in that case, like we'll carve out a proof that looks something like this. Okay, so this is like pictorially what we expect to happen. This is not terribly formal, so let's see if we can make it formal. As always, the most challenging part is to find where I am in my notes, but I think I'm here. Okay, one piece of notation. If a restriction rho satisfies C, then the question is, what is rho restricted? What is C restricted by rho in this case? The way I defined it before, we said, oh, we remove these. Okay. And it turns out that we need to keep track of these guys. And the standard way to do it is to just say, well, this is a trivial clause. We'll denote this clause as 1. Just say this is a satisfied clause. You can think of it as being the clause X or not X or something like this. Just a piece of notation that whenever rho actually satisfies C, I'm going to write that this is the one clause. So now I can treat, this means that when I hit this whole resolution refutation by restrictions, I get clauses everywhere. Except that a lot of, all over the place, I might have this mysterious one clauses, but it's kind of nice to just have to refer to them as clauses also. Okay? So now in the restricted, when I take this proof and hit it with these restrictions, I'm going to get 2 types of clauses. So let me define them carefully. This is an important technical definition. We will have clause types. A Q clause is clause C over Q variables only, and it is derivable from A row Q. Okay? A Q clause is any clause that only contains Q variables and is derivable from the A part of the formula when I plug in rho instead of P. So from now on, like rho is, we're going to think of rho as being fixed. And similarly, an R clause is going to be exactly the same. So it's a clause C over R variables only, and it is derivable from B rho R. Okay? And now the trivial clause is derivable from anything. So we're going to have a lot of different copies of one clauses, and some of them are going to be Q clauses, some of them are going to be R clauses. We'll get there in a bit. Okay, now we'll start with part 2. So we look at our refutation pi, C1, C2, all the way up to CL, that is contradiction. This is pi. We are going to construct a sequence of clauses pi tilde, C1 tilde, C2 tilde, up to CL tilde. And we're going to argue later that CL tilde is actually also going to be contradiction, but we'll get there. And pi tilde contains our candidate refutations. Pi A and pi B. I don't know at the outset which one is going to work. We'll find out. So I'll just start building both, and then when I get to the end, I see which one of them work. we need some inductive hypotheses and see if I can fit them. There are 3 of them. I hope I can fit them on this part of the board. Property 1 is going to be that all of these tilde clauses are P clauses or R clauses. Okay, and I'm going to write this. Let me introduce a notation for the type of a clause. So for every clause I, it is either a Q clause or an R clause. So for every clause, I'm going to classify it as either a Q clause or an R clause, not both. I'm going to do this by induction. And note that this means as soon as I've classified it, I know if it's derived from A or if it's derived from B. Right? Okay, that's property 1. Property 2 is sometimes it's going to be the case that we have to pick the clause, the Ci tilde to be 1. That will only be the case if in the original proof we had Ci and we hit it with rho, then in fact rho satisfied Ci. So my only excuse for making Ci tilde 1 is that actually rho satisfied Ci. But if that doesn't hold, so if Ci tilde is a real clause, which I'll say it's not the trivially satisfied clause, then it also must hold that Ci tilde is a subset of Ci. So the way to think about this is that basically Ci tilde is kind of what you get when you take Ci and hit it with the restriction and remove everything, all the P variables, and then remove all variables that are kind of the wrong type with respect to C. Does this make sense? Is it okay? And then a third, a little bit annoying property that we're going to need. If I have to pick Ci tilde to be 1, then there is an associated axiom, EI. So for bookkeeping purposes, it's going to be the case that EI, this clause, is an axiom clause. It is satisfied by some literal A that rho sets to 1. And this literal A lives in both Ci and EI. Okay, let me write this down and then we'll talk a little bit about this. So, and then I say that EI is an axiom in A or B depending on what type C has. C tilde. Basically, if C tilde has type Q, then EI should come from A over P and Q. And if C tilde has type R, then E should come from the B side. How should we think about this? I mean, picking C tilde to 1 is kind of a little bit uninformative. But basically, what I'm going to, the way to say about this, and suppose somewhere over here, let me do it another color, maybe green. So over here, I had Ci, and it turns out that Ci, when I restrict it by rho, is 1. So I'm going to pick Ci tilde to be 1. then I kind of want an excuse for this. And basically what I'm going to do is the way to think about it, I'm going like to trace, well, this clause was kind of derived, among other things, from this guy. And here is EI. And note that EI is actually also satisfied by rho. And I used EI to derive this clause. And actually the reason that EI is satisfied by rho is still in CI. So it would have been really hard to choose something else. Okay. This is actually what I just said is just fluffy intuition. All we're going to care about from now on are these three formal properties. But this is an attempt at sort of saying why we're going to need it. Because we will be interested in understanding for trivial clauses, when we picked CI tilde to be 1, we want to trace back a reason for that. That's going to come in when we monotonize the circuit. We won't care about it before. So we're just going to carry this around, and then at the very end, we're going to use it. Questions about these technical properties? Like, what is it clear mathematically what they mean? Maybe not the why, but the what.
Could there be multiple EIs that? Because
I'm going to commit to one.
Okay.
So there's a lot of choices here, but I'm going to commit to. For every tilde, I'm going to commit to one type, and then if I chose CI tilde to be 1, I'm going to commit to 1e. There could be several, but I'm going to commit to 1. This is all I need for my bookkeeping purpose.
Mm-hmm.
More questions? Okay, so now just getting ahead of ourselves, suppose that I can know what I'm going to do is I'm just going to inductively classify all the, I'm going to go over this whole proof and build the CI tildes and then classify them. And I claim that if I can do this, we're done with part 2. And also in essentially with part 1. So maybe it's a good to see, is it clear why we would be like, why would this solve our problem? If I can carry out this program inductively. Okay, so note that, can we say anything about what CL tilde is going to be? I claim that CL tilde is going to be contradiction. Why? Well, it could only be it could be 1, except it can't, because it can only be 1 if CL restricted by rho is satisfied, but it's very hard to satisfy contradiction. Okay? So, but then if CL tilde is not 1, then it should be a subclause of this guy. How many subclauses of the empty clause do we have? The empty clause. Okay, so now if we can carry out this program, then CL tilde is going to be contradiction. Now we're done. Why? Because it is either a Q clause or an R clause. All right, so it's either derivable from A rho Q or B rho R. Okay, but then I just look at the label, and then I know whether A or B was unsatisfiable, yes?
Yeah.
Okay, and now it stands to reason, like, how complicated is this going to be? Well, it's not going to be too bad. In fact, it's going to be so simple that once we're done with 2, we're just going to say, okay, Jakob, your proof was so simple that I'll just write down a circuit that does your computations. Basically, I will write down by induction a circuit that computes classification for every clause. And this circuit is going to scale with the resolution proof size. And then you just read off, how does this circuit classify contradiction? And now we're done.
Mm-hmm.
Okay. Obviously, there are a few tiny details to figure out along the way, but it's clear kind of that we're in good shape if we can do this. We still have a problem with monotonicity, and it's going to be a problem. And in fact, this mysterious property P3 is what's going to save us. but we'll get there.
So is it fair to say that what we are really showing is that from the original refutation, after restricting the piece, we exactly get either a refutation from A or from B? Is it going?
We're going to extract a refutation. There could actually be several. There could be, I mean, this restricted formula could and might well contain refutations of both.
Oh, okay.
I'm just gonna, but I am going to extract. So this I don't know. I mean, even for this row, this red guy, it could be. I mean, if rho is such that it also makes A unsatisfiable, then it could be that I have some contradiction down here also. This I don't know.
Okay.
I can't control this. Like I can't analyze this. I'm only able to analyze this guy.
Right. Okay. So it's not just that I restrict and I need to do more.
Yeah, you can. I mean, we know that, right? So I mean, we're getting ahead of ourselves. We didn't learn this. We'll learn like in 2 or 3 lectures from now that if you take any resolution refutation for formula F, and you hit it with the restriction rho, then the sequence of clauses in the refutation pi will, under the restriction rho, that will now, after some moderate massaging, actually be a legitimate resolution refutation of F restricted by rho. But that is not quite enough. Well, we need to be able to extract, we need to know, I mean, this is just an existential statement. I actually need to compute that I know that it's either refuting A or B. And this is what interpolation will give us. So it's sort of the standard fact that restrictions preserve resolution derivation, plus we need to know which part it's refuting. More questions? Or should we get cracking at this? Okay, let's do it. How hard can it be? Okay, base case. Well, basically, we have 2 base cases. We have CI is in A PQ. Like these are for the axiom clauses. Okay. If CI is in A, then I'll just set CI tilde to be exactly CI restricted by rho. And I'll set EI to CI if needed. And I'll set type CI tilde to be Q. Okay, and now let's maybe see, okay, what do we know? Well, the type is correct because clearly if it's an axiom in A is derivable from A. That's right. Okay, good. Excellent. I can do that derivation. Also, I pick CI to be 1 if and only if this restrictive clause is 1. That is like by construction. And it's clear that if CI tilde is not 1, then it's a subclause of CI. That's kind of clear from here also, right? I mean, if actually this is not 1, then this clause is just taking this clause and removing all the falsified literals. Plus, that's, only removing the T literals, right? So this is actually, this is not even like, I guess if CI tilde is distinct from 1, then we actually have equality here, I think, unless I'm mistaken. And okay, but if it is 1, then I pick CI to be its own justification. I mean, it's clearly satisfied and by some literal that is in the clause intersected with itself. So that's also fine. Note, by the way, that when I'm using this, I'm saying that it's a literal that lives in CI intersection EI. Here I'm using what we said in one of the early lectures, that I consider a clause to just be the set of its literals. So that's why I'm using set notation. Okay, and then it's kind of clear, you realize that if CI is in EPR, I'm going to do exactly the same. Let's just write it down. CI is going to be CI tilde, is going to be CI under rho. EI, if needed, is going to be CI. And the type is going to be, the type is R. Okay, done. Okay, inductive step. Now we have that, let's write it this way. So we have CI. It's derived by induction. It's derived by resolution. So it looks like this, derived from some CJ that is C or X, and some CK that is D or not X. All right. And now I will have three cases. Case one is that the variable is in P. Case two is that the variable I'm resolving over is in Q. And case three is that X is in R. Okay? Good. Yes. So actually, let me continue here. Case one is that X is in P. Note that it means that X has a value, right? I restricted X. If rho of X is 0, then that means that I don't have too much choice here. So this is satisfied, but this is not satisfied. So like I have very little information here. Here, CK tilde might be 1 for all I know. But this guy hopefully isn't. So I'll focus on CJ. And I'll set CI tilde to be CJ tilde. And I will set then also the type to be the same. Type CI tilde is going to be type CJ tilde. And also EI is going to be EJ if needed. Or maybe I can always define the EI to be like, I don't know, the empty set if I don't need it, or I don't know. But basically, I'm gonna, if in this setting, if rho made X false, I'm just gonna copy everything from here down. Okay. And now I claim that we satisfy our inductive hypothesis. One is kind of clear. I mean, if CJ tilde was a Q clause, I mean, I just copied it, right? And now, if CI tilde is not 1, then I know that CI tilde is by choice CJ tilde, which is also not 1, which is then inside CJ, right? Except that it's a Q clause. So it's actually inside this, because X is a variable, that's a P variable, and those have been removed. Which means in particular that Cj minus X is inside C or D, yes? Which happens to be Ci. Okay, but okay, so that takes care of if ci tilde is distinct from 1, then I don't need any justification axiom associated ei, and I have subset containment. If instead ci tilde is 1, then I claim that C restricted by rho is 1. Why? Well, I know that this restricted by rho is 1, but x is false, so x is clearly not what rho sets to true, so rho has to set C to 1. And that means that, well, this means that if C already restricted by rho is 1, then C or D restricted by rho is also 1, right? And that in particular means also that if you look at the justification axiom for Cj, so Ej was satisfied by a literal that is common to Cj and Ej, and that is not x. So the justification Ej is good also for this clause. Are we buying this?
Mm-hmm.
Should I say this again? Yes? Okay, let's see if I can say it again. So again, I know that P3 holds for Cj.
Mm-hmm.
And since Cj tilde is 1, I know that Ej is satisfied by some literal that is in both Cj and Ej. Okay? So Ej is satisfied by something in here. Okay? Except not x, because x is false. Okay? So Ej is satisfied by something in here. Ej is satisfied by a literal that is common to Ej and C. Okay, fix that literal. That literal lives in here also, namely in here. That's all I'm saying. Like, okay, maybe. Yeah, so I'm confusing you by making it more complicated than it is.
And you said that the EIs, we only take care of them like...
Well, I just want to carry them along. I won't do anything with them. I just want to carry them along. It's a little bit annoying, yeah. Okay, great. Okay, and now suppose instead that if rho x is 1, then I'm going to do exactly the same. I'm going to set Ci tilde to Ck tilde. The type of Ci tilde is going to be the type of Ck tilde, and Ei is going to be Ek. And really, the argument is going to be exactly the same. I mean, I just run this again syntactically. Whenever you see x, just replace it with not x. Okay? And note for future reference that what did we do now? Well, I said if x is 0, then pick the type from here. If x is 1, then pick the type from here. Is that like, have you seen anything like this before today? Like selectors, maybe? Okay, good. Let's just let's push that on the stack. This observation might come in handy later. Excellent. Case 2. Okay, are we happy with case 1? So I claim that we're done with this case now. Just to stress how done we are, I want to use my green color. Too few colors today. Let's see. Too few figures, I guess, but I had one. Okay, case 2 is that X lives in Q. Okay, so now we get subcases. Depending on type CJ and tilde and type CK tilde. So let's see if we can argue a little bit about this. Basically, okay, let's see if I can get precise. So we're now resolving away a Q variable. Suppose that one of these guys is an R clause already. What would you guys do? We'll just copy it, right? Because if it was good over here, then actually we had already removed X. And you just copy down and everything should be okay. We'll talk about this more. But basically, if one of these is an R clause, take it. Otherwise, if both of them are Q clauses, I might need to do some work. But then I should be fine. The reason I should be fine if both of them are Q clauses, then this is a Q variable. Both of them are derivable. So I should just do a resolution step and I will be good. Okay, this is going too fast. Let's do it again more carefully, and let's see if I got it right or if I messed up. Okay, so but here's case 1. Let's say that one of CK tilde or CJ tilde is an R clause. Yeah, then, as I said, we have already eliminated X, so basically, morally, everything should be fine. So I'm just going to set CI tilde to, say, without loss of generality, CI is this clause. Then I'm just going to set CJ is this clause. I'm going to set CI tilde to CJ tilde. I'm going to copy the type. Assuming again that CJ tilde is an R clause. And I'm going to copy the excuse, the justification axiom also. What do I do if both of them are R clauses? I don't care. Pick one of them. Okay? Pick the first one in that case. Okay. So I claim that property 1 is okay. This is like whenever I copy, property 1 is obviously okay. If it was an R clause before, it is an R clause now. I might need to worry a little bit more about the other properties. So here's my observation now. Now we're doing this a little bit more carefully. So in this setting, CI doesn't contain Q variables. Why? Well, because we copied an R clause, and an R clause only contains R variables. That's like by definition. And X in Q is the only variable that disappears in this resolution step. And this is why, if we just take a deep breath, everything should be fine. Because let's look at so basically, if we're saying that, okay, so suppose was 1, CJ, and CJ was 1 only if CJ restricted by row was 1. Okay, but if so, I mean, it wasn't 1 because of a Q variable, because those aren't even assigned. So clearly it was true because of this guy, and this is something that I'm copying. Okay, and the justification axiom is still fine because nothing happened. And for the same reason, the only thing I need to argue is that I know that, again, I'm going to argue that I know that Cj tilde, if it's not 1, so suppose that it's not 1, then it is contained in C or X. But again, X is a Q variable and this is an R clause. So there is no X variable in there, but that means that it is contained in C or D. Are we buying this? Okay. So basically what I'm saying now is if either of these guys was an R clause, then go with the R clause. Fine. Case B, if either Cj tilde or Ck tilde is a Q clause that doesn't contain X, not containing X, how can this happen? Well, one interesting special case is that one of them are 1. One of them is 1. Okay? Then, again, let Ci tilde be this clause. If one of them is a Q clause that already does not contain X, then pick Ci tilde to be such a clause. If you can pick both, just go with, I don't know, Cj. Okay? And again, you copy Cj, then you copy the type, you copy the justification axiom Ej, and by the same argument as before, the only variable that disappears is X, but X is apparently already gone. And that means that all of these annoying bookkeeping details about justification, whatever row is setting, it is not that variable because that variable is gone. Is actually let me actually I think we can even make this a little bit simpler. We can just say if one of them is a 1 clause, then pick that 1 clause. Let me even change the proof on the fly to be this. Okay. If either Cj tilde or Ck tilde is a Q clause that is 1, then let me copy that 1. So in case C, we're now left with, we have 2 non-trivial Q clauses. Let me write them down. So we have Why they're Q clauses? Well, because we dealt with R clauses in case A. And if one of them was non-trivial, then we dealt, one of them was trivial, then we dealt with that in case B. So case C is, we have two non-trivial clauses. I see now that, I think this is the way we should have been written up, sorry. So again, one of them is an R clause, that's case A. Case B, I think, is one of them is a Q clause, but is trivial. Case C, both of them are non-trivials. Okay, so Cj tilde is non-trivial, so that means that I can write it as Cj tilde prime or x. C. Oh no, okay. Actually, okay. There might be some. I realize now we have a. Sorry, what I said right now was not correct. I'm skipping one case. I want to say, actually, I want to fold into case B. Sorry. I want to fold into case B if one of them don't contain X.
Which is what you wrote, right?
Which is what I wrote. No, that's fine. I stand by. Sorry, I was getting a little bit worried about my bookkeeping, but it's fine. I was okay. Here's what I was worried about. I was worried that we would use the justification literal in the resolution step, but that is obviously not true because the justification literal is something that is assigned. So that's a p variable, and we're only removing q variables here. No, yeah. So I mean, okay. So let me take it back. In case B is when either of them is 1 or either of them doesn't contain X. Then I just copy. Okay, sorry about this. I apologize. So now we're in this setting. Both of them are Q clauses. Both of them are non-trivial. Both of them contain X.
You need a prime on the second CK right there.
If you insist.
I do.
Thank you. Yeah, I would insist if I were you. Okay, so now we just set Ci tilde to be Cj tilde or Cj tilde prime or Ck tilde prime. Basically, we just resolve. Okay. And now I argue, in this case, there's no need to argue about justification. This is a non-trivial clause. And it's clearly, note that this is a subclause of Cj. This is a subclause of Ck by induction, and we're removing X. So this is a subclause of C or D. Right? Are we happy with this?
Mm-hmm.
Fantastic. And now I claim we're done. I mean, we need to do case 3, but it's like completely symmetric. So let me just tell you what we do. Case 3 is going to be if one of Cj tilde or Ck tilde is a Q clause, copy from that clause. Okay. Otherwise, we copy or resolve to get an R clause. It's exactly analogous. Like literally just go over the proof again, change Q for R. Okay, and now I already did, now I claim we're done because this means that we have now successfully classified all of the clauses, including CL. So CL tilde is a Q clause or an R clause. It is definitely not the clause 1, because then I would have found a contradiction, a restriction that satisfies contradiction. So it's not 1. So it's contained, CL tilde is contained in CL, meaning it's contradiction. And it's classified to be a Q clause or an R clause, meaning contradiction has been derived either from A, rho Q, or B, rho R. And if I just go over the proof and do the classification, I will see which one it is. Are we happy so far? Okay, because now we're almost done. Now we just need, now we'll go over this proof again, and we'll argue that it's so simple that it's actually computable by a circuit. So let me identify let me actually, in this case, let me write that type Ci tilde is Q. That means that I identify Q with 0. And if the type of Ci tilde is R, I'll just identify that with a 1. Okay? So R clauses are 1 and Q clauses are 0. Okay? So now I'm going to look at the nodes Vi in my circuit. Okay? And I'm going to be a little bit more generous than we were before. Before, the circuit only had variables and gates. I'm now also going to plug in truth value constants. We didn't have those before. But it's kind of clear that I can build a circuit. I just hardwire some input values and then simplify the circuit, right? I mean, if I have A and B and I plug in a 1 for A, then the sub-circuit simplifies to just B. If I have A or B and I plug in a 1, then the whole circuit vanishes and is replaced by 1. So I'll just bottom up do these propagations until I have a simplified circuit. So are we happy that if I can build a circuit with variables and or select and Boolean constants, then we're good. Then we'll just do a post-processing step. And the circuit size obviously won't go up. We're happy with this?
Yeah.
Okay, perfect. Then, in this case, if Ci is an A clause, then what we did here is we just hardwired this to be the constant 0, right? It's a Q clause. In this case, we hardwire Vi to be the constant 1. It's an R clause. Okay, so for the base cases, all of these, when I build the, basically, I'm now going to actually look at my Boolean circuit. I'm going to plug in 0 for the A axioms, 1 for all the B axioms, and then I'll use rho to sort of build other interesting things. Or rather, actually, rho is what I'm going to compute, though. Sorry. Okay, so case 1 we already talked about. We see that actually Vi is a selector gate that is going to look at X. And if X is 0, then I pick the type of Ci1. Of Cj. And if X is 1, then I should pick the type of Ck tilde. But by induction, this is already computed by node Vj, and this is already computed by node Vk. Right? And note now that, okay, I'm adding, okay, I erased, I guess, the selector now, but you remember that this is like content size get. So clearly, I'm adding, for this step, I'm adding a constant number of gates. We're non-monotone, and that should worry us a bit, but, you know, I'm kicking the can down the road in the hope that you will be too tired to protest in the end. Okay, so that's case 1. Case 2, what did we do? Well, we actually said that if one of them is an R clause, then go with the R clause, and otherwise pick the Q clause, right? So in this case, we actually said that VI is an R clause is one if one of VJ or VK is an R clause, is one. But if both of them are Q clauses, we'll get a Q clause. So this is just an OR gate. Are we happy with this? If one of them was an R clause, if one of them was one, then we're going to be one. If both of them are zero, we're going to be zero. That's an OR clause. Okay? Okay. And now, case 3, we said that I sort of cheated you a little bit on that, but I said if one of them is a Q clause, then copy the Q clause, otherwise take the R clause. This looks a bit like me to say that, well, if one of them is zero, basically, okay, we're going, or let's phrase it differently. The only way you're going to get an R clause is if both of the incoming clauses for the resolution step is R clauses. Otherwise, if one of them is a Q clause, go with the Q clause. Right? Now I built my circuit. So let's see what have we done so far. Okay, I forgot to take those subcases in my inductive step, but now I think that we've built the refutations in 2, and very, very quickly we built the interpolating circuit. And it's kind of clear. Here I added what? Something like 3 or 4 gates. Here I have a single gate. Here I have a single gate. They go of 1. Are we happy? Okay, so now we actually have everything, right? We have 1 and 2. We've done feasible interpolation for resolution. The only thing we don't have is feasible monotone interpolation. And that is a bit of a problem. And let's see what strategically I should do. Maybe erase this. Maybe, let me see, I might even, okay, maybe that was not so good. I wanted the selector on. Okay, now there are 2 cases. So, and I'm just going to do one of them again. Now we're going to do 3. Suppose that the p variables are only positive in a PQ. The other case is going to be like completely symmetric. So what I'm going to do is I'm going to replace all cell XUV gates. Remember, these were like, you had a previous gate U and V, and then based on what the value of X was, we selected. Let's write down what this is. This is, well, if X is false, I take U. And if X is true, then I take V, right? If X is false, then this is true and vanishes, and X is false, I pick U. If X is true, then this vanishes, and I pick V. Okay, so are we happy with that? Okay, so this is the selector thingy. And I'm going to replace it by just X or U and V. I'll go over the whole construction we had before, and I do this replacement. And now I claim we have a monotone circuit. Right? The only problem is this monotone circuit computing correctly? So now we're getting a little bit tired. Maybe in the lecture notes we have. You can build the truth tables of these two, and you see that they're almost the same. There's one line that's wrong. Okay. So you get the following problem: XUV, and here you have cell XUV, and here you have our hack X or U and V. And everything looks perfect, except for 0, 1, 0, where the X says we should select U, so that's what we're going to do. And this guy says that we get a 0. Okay. That is a problem. So whenever in one of our circuits, in some gate we have this input, then we're completely losing control. Right. So we're gonna have. Let's look at this more carefully. So we have Cj, that is C or some P variable. Let me just write it P for now. And we have Ck, that is some D or not P. And Ci is C or D. And we have a row of P is 0. And what do we have more? Actually, let me write it. And we have row of P is 0. And we see that this is an R clause, right? And this is a Q clause. And in our construction, we made sure to pick, what did we pick? We wanted to pick this guy, right? But now in our new proof, we pick this guy. That's kind of, but is okay. So is this a problem? Anyway, let's see. So okay. So basically, we should have. So okay, let's see what we expected Ci to be Cj. We expected type Ci tilde to be R, and then we expected, I guess, Ei to be Ej. And instead, what happened now is that we picked Ck tilde, and we got a Q clause, and we have Ek. Is that a problem? Okay. Not necessarily. So let's see. Suppose Ck tilde is in fact a non-trivial clause, then I claim that we just go through everything again. I mean, copying will always give us a clause of the right type. And we don't have a one clause, so we're not really worrying about P3, this messy thing. And P2 is not going to be a problem because we resolved over a P variable, and that is obviously by the time we define ck tilde, the P variable is gone anyway, and everything is non-trivial, so P2 is fine. Yes? Okay. So if ck tilde is non-trivial, everything is okay. Obviously, we have another case to consider. Now we have nuts because it could be that ck tilde was 1 because of this guy. Unfortunately, that guy is super gone, and C or D over rho is now non-trivial. So copying the justification axiom EK down here is not a great idea, but even more seriously, we could have, so suppose, let's write this down. We could have, the problem I'm worrying about is CI under rho, which is C or D under rho, could be non-trivial, but we have CK tilde 1 because of CK under rho is 1. That would be a serious problem. Can we say anything, what would such a rho be? Well, there's like only one guy, obviously, that, there's only one literal that is missing from here and is in here. So if this is the case, we know that the CK tilde, we know that, not tilde, CK is satisfied by the fact that rho of, rho not, it's getting late in the day. This is supposed to be a P with a negation, I think. So the only way this can happen now is that actually rho set P to true, so this vanished, but P is gone, and this is now not true.
Rho not P is what, right?
Thank you. Obviously, this is just what they taught me at the pedagogical course to do, just to see if you're aware. But you already knew that. Thanks. Okay, this is what is happening. This is very interesting. So now let's go back to, why did I pick CK tilde to be 1? Well, I was justified to do that because there was, in fact, apparently there was an EK such that EK was in, what type was it? It's a Q clause, right? So EK is in a PQ. EK under rho is 1. And I know that, what do I know more? I know that EK, let's write this down very carefully and see if I got it right. EK is satisfied by a rho of the row A1 for an A that is in both EK and CK. And currently not in C. Right? Because again, rho is not satisfying this guy. So what is the only literal that rho can satisfy? Again, I'm circling back to i.e. A is actually not P. That's the only possibility. How happy are we with this? Should I say it again? I feel I'm like messing this up a little bit. Should I say it again or?
How do we know that EK is under row is 1? Was that part of our?
That's part of P3. If I chose, now my I is K here. So C K tilde is 1. Then there is an EK. And EK is satisfied by some literal that lives in both CK and EK.
Good.
Okay. And furthermore, EK is of the right type, which is type Q here. So EK in our setting here, yeah, this is like, I mean, we're so close to the finish line now, so it's worth. So here is EK. EK in this case is a Q clause. And it's satisfied by our row of A for some A that lives in both CI and E, lives in both CK and EK. But rho is not apparently, again, where do we have the resolution stuff? Rho is not satisfying D. Right? Rho is satisfying this guy, but apparently D under rho is not 1. Because otherwise, if it were 1, I wouldn't be too worried. Right? So it has to be this guy. And now I claim we're done. Because I found an axiom in A that contains P negated. That's a little bit surprising, isn't it? Someone promised to me solemnly that there would be no negative occurrences of P in A. Now, it is true that if I ever had an input like this in my circuit, then I would screw up, potentially, but I can never have such an input. Because the structure of my input CNF formula is such that this case can never arise. So we're good. And now you can ask, like, okay, what if the other case? And now you have to think about it a little bit. I think now, okay, what if we have the other case? I still think that, but maybe we should think about this carefully online. I think you could probably just swap the roles of P and Q and sort of flip all the signs, and then you need to think about, am I now getting something monotone or something anti-monotone? But I think you can rename like the original problem. Or you can just basically figure out, you're going to get a similar hack like this, which I don't even remember what it is. But it's like completely similar. And now we're done. And this means that we now did enough hacking to get this. And then you said before the break, if we had this structural theorem, then we observed that the clique-colouring formula, again, just repeating what we said right before the break, the clique-colouring formula satisfies these conditions with some margin, right? Because we know that P is only positive in A, only negative in B, so that's like by a wide margin, all that we need. So, again, if we have, suppose we have a resolution refutation in length L of clique-colouring formulas, then we run it through this theorem by Pudláks, and we extract an interpolating monotone circuit for this formula. such an interpolant, if I promise to feed it, like if this interpolating circuit gets a graph that actually has a clique, it has no choice but to answer 1, right? The graph has a clique, it's not colorable. If this interpolating circuit gets a graph that is in fact m-1 colorable, it has no choice but to answer A is false, there is no clique. Okay, so now we have a monotone circuit that is distinguishing the cases that Razborov and Alon-Bopana considered, and has the same size as the resolution refutation. But now Razborov and Alon-Bopana says that this monotone circuit has to be exponentially large. Hence, our resolution refutation is also exponentially large. Done. Okay. And now, what will happen when we go over to cutting planes? Well, for cutting planes, we won't be able to extract a standard circuit. We will actually extract some kind of weird circuits that compute with real valued numbers. But that is still monotone in the sense of what a standard function, like what is a monotone function? Well, it's a growing function. And then you say, oh, well, this is bad. This is like a much more expressive circuit. But then you take a deep breath and go through Razborov's lower bound, and you check what happens with these kind of model of real valued circuits, and you observe that, oops, I guess the proof just goes through. And then you get a cutting plane slope. But that is something that we will not do today. So any questions before we wrap up?
Yes. Do we have other classes of standard classes of formulas that fit this framework?
Excellent question. And the one other example I know of is there's a paper by Cook and Haken, and they constructed something that is called broken mosquito screen formulas. And I just realized that I might be a little bit too tired to remember exactly what the broken mosquito screen formulas are. But basically, you say that you have a set of somehow you have a set of elements that you can partition in 2 different ways that are inconsistent, and then you and when you encode this as a CNF, you will get the same kind of property. Now, interestingly, the Copenhagen paper just studies the computational problem, like the broken mosquito screen input, basically, which is, again, looking for a circuit that computes which one of the 2 partitions doesn't work. And then they say, oh, you can also turn this into a CNF formula lower bound for Kelly planes, but they don't even write down the CNF formula. They don't write down the encoding. And I wasn't able to track down any other paper. Lots of other papers cite this CNF formula lower bound, but they don't even write down what the CNF formula is. And I think when I try to write it down, I think what happens is that these broken mosquito screen formulas get ridiculously large, ridiculously fast. But apart from broken mosquito screens and clique-colouring, I'm not sure if I know. What I do know, and this is interesting though to note, that this is sort of a parallel discovery. This idea of interpolation, of feasible interpolation, is used a lot, I think, in formal methods and formal verification. Like there are people who actually do things like when you verify what is it, like hardware or software systems, things like this. I'm out of my comfort zone now by some margin, but basically for reasons that I don't remember right now, these people do want to compute interpolants. But then typically they actually want to use, like, it's a little bit, again, they're using the positive direction of this, that once your solver has solved the problem and your solver ran somewhat efficiently, that means that from the solver run and the solver computations, you do extract an efficient interpolation and you're happy. And as usually in computational complexity theory, we turn the tables on this. I mean, again, practitioners reduce to SAT because they can solve SAT. And so that gives them a way of solving all of these other problems. And what we prove is that basically the other way, that since we believe that SAT is hard, that shows that all of these other problems are. So sort of Pudláks turns the table of interpolation and uses it as a lower bound technique, whereas over in formal methods, it's used as a constructive technique to actually compute interpolants that you can use. So interpolation is being used heavily. Improved complexity, I don't know if, yeah, I guess we'll have to take this as homework. Clique-colouring, broken mosquito screen.
The reflection principle for resolution.
The reflection principle for resolution, okay. I mean, there are also some version of clique-colouring that is co-clique. That is somewhat similar, but not exactly the same. Yeah. More questions? Okay, then maybe we'll call it a day. Thank you.